Hi everyone! This is Professor M. Does Science, and today we're going to solve the eigenvalue equation of the Hamiltonian of the hydrogen atom in another one of our videos on rigorous quantum mechanics. The proton and the electron in the hydrogen atom interact via an electrostatic potential. Their interaction is described via a differential equation, the eigenvalue equation of the Hamiltonian. To understand the properties of hydrogen, we need to solve that equation and calculate the energy eigenvalues and eigenfunctions. And that is precisely the plan for today's video. The solution is rather interesting and it takes the form of a para series. Today we're going to focus on the mathematical solution, and I have to confess that it is rather long, but I promise you that it is worth doing it at least once. While today's focus is on the maths, I really encourage you to check out the other videos in the hydrogen atom series to gain a more conceptual understanding of the system. So let's go! Let's think about the hydrogen atom. Hydrogen is made of two particles, a proton and an electron. In the introductory video on the hydrogen atom, linked in the description, we discuss how the important physical content of the system is encoded by the relative motion of the proton and the electron. This means that we can describe the hydrogen atom using an effective one-particle relative Hamiltonian, which has a kinetic energy term and a potential energy term. For the full details about this relative Hamiltonian, check out the introductory video on the hydrogen atom. But in short, mu here is the reduced mass of the system and is related to the individual masses of the proton and electron by this equation. P here is the relative momentum, given by this expression in terms of the individual momenta of the proton and electron. And R here is the relative position, given by the distance between the proton and electron positions. The Hamiltonian is the key to understanding the hydrogen atom using quantum mechanics, and the aim of this video is to describe the mathematical solution of its eigenvalue equation. In particular, we're going to consider this problem in the position representation, so we can rewrite the relative Hamiltonian as equal to the kinetic energy term in the position representation, plus the potential energy term in the position representation. An important observation is that the potential of this system is a central potential. We have a full series of videos where we discuss the general properties of central potentials, and today we will exploit many results from those videos in solving the Hamiltonian eigenvalue equation for hydrogen. So I encourage you to check them out if you haven't yet. For completeness, we can also write down the relative Hamiltonian by spelling out the kinetic energy term in spherical coordinates, and as discussed in the video on central potentials, it is given by this prefactor, multiplied by a term that involves the derivative of r, and then a long term that involves the derivatives of the angular variables, and finally, don't forget the potential energy term. But before we start with the maths, two additional points. We discussed in the introductory video on the hydrogen atom how the large mass difference between the proton and the electron means that the relative motion of the two particles is such that the proton is almost at the centre of mass, and therefore the relative motion is very close to the motion of the electron about the proton. This insight is very useful to help us conceptually understand hydrogen, and it is useful to think of this relative Hamiltonian as simply describing the motion of an electron in an electrostatic potential generated by a stationary proton. The maths, of course, still describes the true relative motion of the two particles. Second, to simplify notation, from now on we're going to drop the rel subindex here and simply write h for the relative Hamiltonian. Using this Hamiltonian, we can build its eigenvalue equation like this. In this equation, these are the eigenvalues and these are the eigenfunctions. In the videos on central potentials, we learned that the Hamiltonian of a central potential commutes with the orbital angular momentum operators. This implies that the eigenfunctions of the Hamiltonian can be chosen to also be eigenfunctions of the squared orbital angular momentum and eigenfunctions of the z component of orbital angular momentum. Remember that in the L squared eigenvalue here, L can only take non-negative integer values, and that for the Lz eigenvalue here, and for a given L, ML can only take one of these values separated by integer steps. If you need a refresher about orbital angular momentum, you can find all the relevant videos in the description. Another important result from the videos on central potentials is that the common eigenfunctions can be labelled by three quantum numbers, k, l, and ml. L and ml are the quantum numbers associated with orbital angular momentum, and k describes the energy spectrum for a given L and ml. The energy eigenvalues can be labelled with k and l, but they don't depend on the ml quantum number. Another important observation from those same videos is that these three equations imply that the common eigenfunction psi is a product of a function r that only depends on the radial coordinate and another function y that only depends on the angular coordinates. These functions y are called spherical harmonics and are labelled by the angular momentum quantum numbers L and ml. For more on these spherical harmonics, we have a video dedicated exclusively to them, and the link is in the description. What we care about today is that the spherical harmonics are the same for any central potential. This means that we've already solved half the problem before we've even started, because the angular part of the eigenfunctions of the hydrogen atom is given simply by the spherical harmonics. This other part here is called the radial part of the eigenfunction, and it depends on the quantum numbers k and l, but it does not depend on ml. This radial part is the most interesting part, because its form depends on the specific central potential that we have, and therefore the aim of today's video is to determine this radial function for this specific example of the hydrogen atom. The strategy we'll follow for the solution is actually very similar to the one we use in another central potential problem, the 3D isotropic quantum harmonic oscillator. So I would recommend that you check out that video for another example of solving eigenvalue equations of Hamiltonians that describe central potentials. So, our mission for the rest of this video is simply to determine the radial part of the eigenfunctions. As we learn in the videos on central potentials, the radial function obeys the radial equation. This equation has a term that involves derivatives in the coordinate r, a term that depends on the L quantum number, and the central potential, which in our case is the electrostatic potential, all acting on the radial function and equal to the energy eigenvalue multiplying the radial function. The energy eigenvalues here and the radial functions here only depend on the k and l quantum numbers. This is the first step of our solution. As we already know the angular dependence of psi, we can reduce the full eigenvalue equation for psi to this new differential equation that will allow us to determine the radial part. The first step is one that is common to the solution of every single central potential. It is convenient to make a change of variables such that the radial function is equal to 1 over r times the new function u. We can then rewrite the radial equation for the function u as given by this very long operator acting on the u function and equal to the eigenvalue times the u function. What is the point of this change of variables? The equation for u is simpler than the original equation for r, because this differential operator here has a simpler form than the original one up there. But this equation is not enough. To ensure that we get physically valid solutions, we need a boundary condition on u, such that when we evaluate it at the origin, we get 0. This discussion so far is the same for any central potential, and we're not going through every single step in detail because we've already done so in the videos linked in the description. Today we will actually solve this differential equation to determine the form of u for the hydrogen atom, and once we have u, we can use it to calculate the radial part of the energy eigenfunctions from this relation up here. Before we actually tackle this differential equation, we need to discuss two additional topics. This term here looks like the kinetic energy of a particle moving in the one dimension labelled by the direction r. We can also combine the L-dependent term with the electrostatic potential and collectively call them an effective potential. As we discussed in the video on the radial equation of central potentials, this now looks like the eigenvalue equation of the Hamiltonian of a particle moving in 1D and subject to this effective potential. While we know that in reality we have a 3D system, and that the true potential is simply the electrostatic potential here, this effective view provides a useful tool to understand the problem. One of the convenient features we gain by treating this as a 1D problem is that we can easily visualize it on a pair of axes. We have the coordinate r along the horizontal axis and the true potential along the vertical axis, yielding this diagram. We can then plot the effective potential for the different values of L, trivially getting the original potential when L equals 0, this effective potential when L equals 1, this one for L equals 2, and we would get similar shapes for the effective potential for all other values of L. Now, what's important for our purposes today is that all of these potentials asymptotically approach 0 from below as r increases here. Building on from the videos on bound and unbound quantum states, we know that this type of potential leads to two types of solutions for the eigenvalues and eigenstates of the hydrogen atom. For positive energies, say somewhere here, the motion of a classical particle moving in these potentials is unbounded, as for large r, the potential tends to 0. In this situation, for a quantum particle, we get what are called unbound states. The corresponding energy spectrum of a quantum particle is continuous, and the corresponding eigenfunctions are not square integrable as they do not vanish for large r. By contrast, for negative energies, say somewhere here, the motion of a classical particle moving in these potentials is bounded, as the particle's energy is lower than the potential at large r. Correspondingly, we get bound quantum states. This leads to a discrete energy spectrum for a quantum particle, with associated square integrable eigenfunctions that vanish as r becomes large. The focus of our video today will be to find the spectrum of the bound states of the hydrogen atom, so we will exclusively focus on negative energy eigenvalues. And a final step before we solve the differential equation, with the aim of simplifying notation. First, let's define a new quantity A0, equal to 4 pi epsilon 0 h bar squared over mu e squared. A0 is called the reduced Bohr radius, and you should check that it has units of length. For our purposes today, this is a purely pragmatic definition that will allow us to simplify notation, but as we study the hydrogen atom, we will see that the length A0 actually has an important physical meaning, because it is a measure of the typical atomic dimension. Second, let's define another quantity E sub I as equal to mu over 2h bar squared, multiplying E squared over 4 pi epsilon 0 all squared. E sub I is called the ionization energy, and you should check that it does indeed have units of energy. Again, today we will simply treat this as useful definition, but E sub I also has an important physical meaning. It is the energy needed to unbind an electron in the ground state of a hydrogen atom. We're now going to use these definitions to simplify the differential equation at the top. First, let's multiply both sides of the differential equation by this term. Moving down here, we obtain this new derivative term, this new L-dependent term, this new potential term, and we're also moving the eigenvalue to this side of the equation, all acting on U and all equal to 0. I have rewritten some of these terms in a form that will prove convenient in a moment, so feel free to pause here and cross-check this step. Moving on, we now see that this term here is A0 squared. This term here is also A0 squared. this term here is a0, and this term here is the inverse of ei. This means that we can rewrite the differential equation in a much simpler form. We first have this differential term, then the L-dependent term, then the potential term, and then the energy eigenvalue term, all acting on U, and everything is equal to 0. Note that in this latest expression, I've also multiplied by -1 for convenience. And a final simplification. Let's define rho as equal to r over a0, and lambda as equal to the square root of minus the eigenvalue over e sub I. At first sight, this minus sign here may look strange, but remember that we are looking for energy eigenfunctions of the hydrogen atom that correspond to bound states, and bound states have negative energy eigenvalues. Therefore, the argument of the square root is overall positive, making lambda a real quantity. With these definitions, we can now rewrite the differential equation in terms of rho and lambda like this. And feel free to pause here to double check this change. And now I hope you will agree that it's been worth making these changes, as this latest expression for the differential equation is very compact, which will prove helpful when doing the maths. Conceptually, though, what we've done is to simply use the reduced Bohr radius here as a unit of length, and the ionization energy here as a unit of energy. To solve this differential equation, we first consider its asymptotic behavior in the limit of rho going to infinity. In this limit, we have that this constant term dominates over this term that has rho in the denominator, and over this term that has rho squared in the denominator. This means that in this limit, we can approximate the full differential equation as containing the derivative term and the constant term, all acting on the function u, and all equal to 0. We've ended up with a standard second-order linear homogeneous differential equation, and the two solutions for u are this positive exponential and this negative exponential. If you aren't convinced, feel free to plug in these solutions into the differential equation to confirm that they are indeed the solutions. These two solutions are, of course, not the full solution of the problem because we're neglecting two terms in the differential equation. However, this analysis tells us that the solutions in the limit of large rho behave like exponentials. And this is an important insight because of the two solutions, only the negative exponential here is in fact a physically acceptable solution. This is because the other solution diverges for large rho and would lead to solutions that cannot be normalized. So how can we use this knowledge? Going back to the full range of allowed values of rho, we can now draw inspiration from the asymptotic behavior and write the true u function as equal to the negative exponential times a new function v. And what do we accomplish with this change? We know that the solution must behave like a decaying exponential in the limit of large rho, so by singling it out here, we are hoping that this will lead to simpler maths, and indeed we're going to find that this is the case. But before we go on, note that by singling out the negative exponential, we haven't actually removed the unphysical positive exponential solution, so we will still have to deal with that later on. Okay, so let's next rewrite the differential equation with this latest change. Remember that the function u is equal to this exponential times the new function v. The harder term is the derivative here, so let's write the second derivative of the new expression in terms of v. Using the chain rule, we first get the term involving the second derivative of the exponential multiplying the v function. Then the cross term, which is 2 times the first derivative of the first term, times the first derivative of the second term. And finally, the term involving the exponential and the second derivative of v. The second derivative of the exponential with respect to rho easily evaluates to this, and the first derivative of the exponential with respect to rho easily evaluates to this. Putting everything together, we start with the exponential common factor, then considering this first term up here, we get a term proportional to the function v. From this middle term up here, we get a term proportional to the first derivative of v. And from this final term up here, we get a term proportional to the second derivative of v. We are now ready to rewrite the differential equation up here in terms of the v function. First, we can use this expression we just calculated to replace the second derivative term all the way up here. Doing so, we end up with the common exponential factor, and we then copy the long expression we just derived. Going back to the full differential equation, we then have the L-dependent term, then the term arising from the electrostatic potential, and the term arising from the energy eigenvalue, all acting on V and all equal to 0. Finally, we can remove the common exponential factor as we are equating to 0. And we can also cancel this lambda squared here with this one here. Overall, we end up with the second derivative term, the first derivative term, and these two terms that don't involve derivatives, all acting on V and all equal to 0. So, solving this differential equation will give us the function v. But we need an extra ingredient. Remember that we had a boundary condition for the function u such that it vanishes at the origin. As u and v are related by this expression, we can straight away conclude that we get an analogous boundary condition for v. Before we launch into the final push for the solution, let's recap where we're at. Solving this equation, we'll find the function v that depends on rho. Once we've got v, we will be able to build u using this relation between the two. And also going back from rho to r using this relation. And once we've got u, we'll be able to calculate the radial function r using this relation between the two. Finally, once we've got the radial function, we will be able to construct the full eigenfunction psi using the standard separation in terms of radial and angular paths. This may look like a rather convoluted path to determine the eigenfunctions, but they obey a rather complex differential equation to start with, so we had no reason to expect a straightforward solution. Okay, so we're now ready for the final push. Let's figure out what v is. We will write v as a power series. We set it equal to rho to the power s, and then a power series in rho. We can also rewrite it by taking the power s inside the sum. Without loss of generality, we start the sum at q equals 0, which means that we choose C0 to be the lowest non-zero expansion coefficient, so that the lowest power in the expansion is this s here. This choice will not affect the final answer, but it's a convenient way to write the power series. Let's first look at the derivative terms. For the first derivative of v, we can rewrite it as the derivative of the power series, and as the derivative is a linear operation, we can simply calculate the derivative of each term in the sum to get this new sum. For the second derivative of v, we have that it is equal to the first derivative of this expression we've just derived, and we again evaluate the derivatives of each term in this series to get this other series. We now have all necessary ingredients to rewrite the differential equation at the top in terms of the power series. Every term will have the summation over the c coefficients, so we can start with that. We then have the second derivative term at the top here, which is given by the second derivative of the power series we've just derived. Moving to the second term at the top here, we have this prefactor, and then the first derivative of the power series, and moving to the next two terms up here gives this expression times the power series. And finally, all of this is equal to 0. Let's briefly recap. Starting with the differential equation for v at the top here, we have then expanded v as a power series in rho, as shown here, And this is the expression we get for the differential equation when plugging in the expansion of v. To simplify this further, we can combine this factor of rho squared with this power over here to get a power of q plus s minus 2. And we can also combine this factor of rho in the denominator here with this power over here to get a power of q plus s minus 1. We can then rewrite the whole expression with the same sum over CQ, and then grouping together the q plus s minus 2 powers, and then the q plus s minus 1 powers, and all is still equal to 0. Feel free to pause here to make sure of this step, but all we've literally done is to rearrange the terms. Next, we consider the boundary condition at the top here. Writing v as a power series, we can impose the boundary condition by evaluating it at the origin, and then setting it to 0. So how can we ensure that this equation holds? We must have that s is strictly larger than 0, otherwise we would get a constant non-zero term in the sum that wouldn't vanish at the origin. So, putting everything together, the power series expansion coefficients must obey this equation at the top, and the boundary condition implies that s is positive. The only way in which a full power series can equal 0 is if the coefficients in front of every single power vanish. Now, inconveniently in the expression that we have here, every term contains two different powers, q plus s minus 2 here and q plus s minus 1 here. This means that we need some extra work to clearly identify the coefficients in front of each power. And to see what's going on, let's consider the first few powers explicitly. To simplify notation, I will call this first term AQ and this second term BQ. Let's start with the lowest power in the series, s minus 2. The term proportional to the A coefficient here gives a power of s minus 2 when q equals 0, which means that we end up with this term proportional to C0. For the term proportional to the B coefficient here, the lowest power in this term is s minus 1, so it doesn't make a contribution to the s minus 2 power. As the coefficients of each power must vanish, then these coefficients of the power s minus 2 must be equal to 0. The next power is s minus 1. The A term gives a power of s minus 1 when q is equal to 1, and we have this term proportional to C1. Now, the B term does contribute with its lowest power, corresponding to q equals 0, and giving this term proportional to C0. So this is the full coefficient in front of the power s minus 1, and it must also vanish. We could go on like this, term by term, and the general power q plus s minus 2 has contributions from the A term proportional to CQ, and from the B term proportional to CQ minus 1. And again, these coefficients must vanish. What do we learn from this set of equations? We can solve them to determine the expansion coefficients of the v function written as a power series. So this is what we need to do. Let's start with the first one, corresponding to the power s minus 2. So this is the first equation that the expansion coefficients must obey. Using this expression up here for a sub q, we can write down 8 explicitly by setting q equal to 0. And we get s times s minus 1 minus l times l plus 1. We can now insert this expression for a naught into the equation up here, and we get C0, multiplying the expression we just got for a naught, and all equal to 0. Remember that by definition, C0 is the first non-zero coefficient, which means that this bracket must vanish to obey this equation. In principle, there are two possible solutions. Either s is equal to minus l, or s is equal to l plus 1. However, we've established earlier that the boundary condition that forces the function v to vanish at the origin implies that s must be strictly larger than 0. Combined with the fact that the quantum number L is non-negative, then these two results together mean that the first solution up here is not consistent with the boundary condition. As a result, the only valid solution is s equal to L plus 1, and this result fixes s. Going back to our set of equations, we're now ready to look at the general power q plus s minus 2. We have to use this equation here, and we start with cq, then we use the expression for a up here to write down its value at aq. Then we add cq minus 1 and use the expression for b here to write down the expression for bq minus 1, and all is equal to 0. We've just shown that s equals L plus 1, and using this expression for s here, here, and here, we end up with this term proportional to the cq coefficient, and with this term proportional to the cq minus 1 coefficient, and all equal to 0. We can now take this bracket proportional to cq, and we copy it down. Multiplying the first two brackets through, we get these 4 terms, and we also have to subtract the final L times L plus 1 term. We can now cancel this term with this term, and we end up with a common q factor multiplying q plus 2L plus 1. And feel free to pause here to double check this step. Bringing everything together, we end up with this long expression that describes a recurrence relation between the CQ and the CQ minus 1 expansion coefficients. Let's recap. We're trying to solve this differential equation up here, subject to this boundary condition on the right. We have postulated a solution in the form of a power series like this. And we've now concluded that the expansion coefficients in this power series must obey this recurrence relation between CQ and CQ minus 1, where I've somewhat rearranged the expression we got in the previous slide. Remember also that C0 is different from 0 by definition. What this means is that starting from a general expansion coefficient CQ, we will be able to use the recurrence relation to end up writing it as proportional to C0. We won't do this just now, as it will be easier to do after we've determined the possible values of lambda here. But as we can in principle do this for any expansion coefficient, we will be able to write the full power series in terms of the C0 expansion coefficient. Finally, we will be able to fix C0 itself by normalizing the resulting wave function. The next question that we explore is whether the series is finite or infinite. Mathematically, we can have both options, but we will see in a moment that only a finite series gives physically valid solutions that can be normalized. To explore this question of normalization, we will first suppose that we have an infinite series. To be absolutely clear, remember that we are considering the series expansion of the v function like this. In this case, we can take the limit of large Q for the ratio of CQ over CQ minus 1. Using this expression up here, the dominant term in the numerator is 2 lambda Q, and the dominant term in the denominator is Q squared. Simplifying, we end up with 2 lambda over Q. What does this mean? If we have an infinite series, then for very large Q, the ratio of consecutive coefficients tends to this value. Let's hold this thought and we will come back to it in a moment, but first we need an extra ingredient. To understand the implications of the limit we just discussed, we will now show that it is the same limit as that of a rather simple function that we can easily analyze. Let's consider the power series expansion of this exponential. We can write the exponential as this sum over q of the usual power expansion for an exponential, And for convenience, we're going to rewrite it as the sum over Q of an expansion coefficient AQ times the power where we identify AQ with the original expansion coefficient. We can now calculate the ratio AQ over AQ minus 1. Plugging in this definition, we get this for the numerator and this for the denominator. The 2 powers simplify to 2 lambda, and the 2 factorial terms simplify to q in the denominator. In the limit of large Q, we end up with the same ratio we had on the previous slide. Right, let's go back to our series expansion for the function v. We've just established that if we consider this exponential as a power series, then the limit of large Q for the ratio of consecutive expansion coefficients is equal to this expression. Now, these two expansions are slightly different because this power of s here in the first expansion is not present in the expansion of the exponential. However, all this extra power s does is to provide a shift in the comparison of the expansion coefficients between the two series, and such a shift becomes irrelevant in the limit of q tending to infinity. Overall, this means that both series have the same limit for large Q. And in turn, this means that if our series expansion for v is infinite, then the v function behaves like this exponential for higher order terms in the expansion. And this is where we have a problem. This exponential has a positive argument here, so it becomes increasingly large for large rho. This means that this v is a physically unacceptable solution because the resulting wave function would not be normalizable. And therefore, the key question becomes, how can we avoid this unphysical solution for v? And of course, the answer is that physically relevant solutions correspond to power series with a finite number of terms. Before we explore what that means, a quick aside. Having an infinite series is a mathematically valid solution that leads to the physically invalid solution we already found when we solved the differential equation in the limit of large R, but now it is appearing for the full equation. So we need to ensure that this power series is finite. To do so, all we need is to find an expansion coefficient term, say the kth expansion coefficient, such that ck vanishes. Given the recurrence relation up here, this immediately implies that all higher expansion coefficients also vanish, and the series becomes finite as required. So the question now is, how can we ensure that ck vanishes? This will happen if the numerator up here is equal to 0 when q equals k. Explicitly, the series will terminate if lambda times k plus l minus 1 is equal to 0. Rearranging, we get that lambda is equal to 1 over k plus l. At this point, it is important to note that I've conveniently labelled by k this integer index at which the series terminates. This is because this is a number we can use to label the different eigenvalues for a given L, and we had already decided to call this quantum number k, so I am now using this label. Finally, remember from earlier in the video that we defined lambda kl as equal to the square root of minus the energy eigenvalues ekl divided by the ionization energy ei. Rearranging, we get that the energy eigenvalues are equal to minus ei times lambda squared. And using the result we just found for lambda up here, and inserting it in this expression, we get minus ei over k plus l squared. Also, remember that l is a non-negative integer, and as c0 must be different from 0 as shown up here, this means that k must be strictly larger than 0. And this implies that the allowed values of k are positive integers. So, by insisting that the series must be finite, we have now come to a key result. The energy eigenvalues of the bound states of the hydrogen atom are quantized, and the energy levels are given by this expression. Now, this is a hugely important result, but we won't explore it any further today as we're only focusing on the maths. However, you can check out the videos that we have linked in the description, and they have a lot more information and discussion on these energy eigenvalues. We're now ready to go back to our recurrence relation and determine the values of the expansion coefficients in terms of the first coefficient C0. To do so, we're first going to simplify the expression we have for the recurrence relation by inserting this value of lambda inside this expression. Doing so, we get the ratio of CQ to CQ minus 1 as equal to this numerator, where I am already inserting the value we have for lambda over this denominator. If we now focus on this term in the numerator, we can copy it down. We can then combine the two terms to get this. We can now cancel the L here with the 1 here and end up with this expression. Going back to the recurrence relation at the top, we can rewrite it like this, where I am doing some trivial rearrangement. And this is the simpler recurrence relation that we will use moving forward. Let's start by copying the recurrence relation where I am moving the CQ minus 1 factor to the right, as it will prove convenient in a moment. Next, we want to use the recurrence relation again, but now write CQ minus 1 as equal to the corresponding fraction times CQ minus 2. Do pause here to double check this step. All we've done is to replace Q by Q minus 1. Inserting this expression inside the one above, we first get the Q independent terms, which now appear to the power 2, and then this long expression with the Q dependent terms times CQ minus 2. This now gives us a relation between CQ here and CQ minus 2 here, and we now play the same game again and again until we arrive at CQ equal to the power Q of the Q independent terms. Then this very long expression involving the Q dependent terms and all multiplying C0. And again, feel free to pause here to make sure of this latest expression, which may require you writing out a few more terms explicitly before it clicks. The final step is to first pick this term in the numerator here, which we can rewrite to this expression in terms of a ratio of factorials, this term in the denominator, which is simply q factorial, and this other term in the denominator, which again we can rewrite in terms of another ratio of factorials. This allows us to write the final expression for CQ as equal to minus 1 to the power q, multiplying 2 over k plus l all to the power q, multiplying these two fractions involving factorials, and all multiplying C0. And finally, we have a general expansion coefficient CQ in terms of C0. And that's it. After this incredibly long and mathematical derivation, we now have all the ingredients that we need to study the energy eigenvalues here and eigenfunctions here of the bound states of the hydrogen atom. So we'll now finish with a brief summary of the key results, which we then use in other videos to explore from a more physical perspective the meaning of the eigenvalues and eigenfunctions. So, the full eigenfunction psi is equal to the product of a radial part and an angular part. The angular part is given by the spherical harmonics because the Hamiltonian of the hydrogen atom commutes with the orbital angular momentum operators. The radial part is the trickier part to determine, and we've done just that in this video by solving a rather complex differential equation. Doing so has required a large number of steps. First, we've rewritten the radial function in terms of a new function u like this. We've then made a change of variables to rewrite u as a function of a new variable ρ, where ρ is the ratio of r and the reduced Bohr radius. Then, by considering the limit of large ρ, we've defined yet another function v, which is related to the u function via this relation. and where lambda is defined as equal to the square root of minus the eigenvalue over the ionization energy. Next, we've expressed the function v in a power series like this, where the exponent s is equal to L plus 1. And finally, we've shown that the expansion coefficient CQ is related to the expansion coefficient C0 by this rather long expression. We can then complete the solution by fixing C0 through normalizing the wave function. And this is it. This is all we need to determine the eigenfunctions. Once we've determined these C expansion coefficients, we can construct V. Once we have V, we can construct U in terms of the rho variable. We can then go back to the original coordinate R. And once we have U like this, we can construct the radial function. And once we have R, we can finally build the eigenfunctions. With this recipe, we can now build any eigenfunction we want. And you can find examples of this in the videos linked in the description. Okay, so if you've made it this far, know that this is our longest video so far. So thank you for sticking around. I encourage you to check out the rest of the videos on the hydrogen atom series to gain a more conceptual understanding of the mathematical solution that we've derived today. And as always, if you liked the video, please subscribe.